Hi, it's Dr. Robin, aka Double O Pi. In this video, I'm going to give you a brief introduction to Beer's Law. And specifically, I'm going to be talking about the application of Beer's Law to UV-Vis spectroscopy, but just so you know, it also applies to other sorts of spectroscopy, like infrared. Before we get into Beer's Law, you need to understand the difference between transmittance and absorbance. We'll start with transmittance because it's the easiest to understand. If you think about what happens as light passes through a substance, there are really only two possibilities. Either the light passes straight through the substance without changing its path, or it interacts with the molecule and its path changes. As a general rule, light that is leaving a substance will have a lower intensity than when it entered. In other words, if you put a certain number of photons into a substance, you will get a smaller number of photons out. Transmittance is defined as the ratio of the intensity of light leaving the substance divided by the intensity of the light entering the substance. In this cartoon, we have 4 photons entering the substance and only 1 coming out. So our transmittance is 1 divided by 4, or 0.25. We also sometimes talk about the percent transmittance, which is just the percent of the original intensity that exits the substance. Here, that's 25%. So that's transmittance. What's absorbance? That's a quantity that's defined as the negative log of transmittance. Out of context, that sounds like a weird factor to use, but we'll talk about why it's useful in a little bit. Let's look at how transmittance, percent transmittance, and absorbance are related to each other. The highest value you can have for transmittance is 1. That corresponds to a percent transmittance of 100%. Basically, all of the light gets through. The corresponding absorbance value is 0. In other words, no light is absorbed because all of the light is getting through. A transmittance of 0.1 corresponds to 10% transmittance, which means that 10% of the light is getting through. The corresponding absorbance value would be 1 there. And then a transmittance of 0.01 is a 1% transmittance, which also corresponds to an absorbance of 2. So you could see that as the transmittance value decreases, the absorbance value increases. We try not to get readings above an absorbance of 2 because it means that very little light is getting through, which makes it hard to quantify anything accurately. We'll get to the equation that's associated with Beer's Law in a little bit, but you should understand the basics about why it works. What affects how much light is transmitted? First of all, it's dependent on the substance that the light is passing through. This is probably fairly obvious to anyone who has observed the world. A lot of light passes through glass, while a lot less passes through curtains. Secondly, when we're talking about solutions, the transmittance depends on how concentrated a substance is within that solution. You've probably noticed this in rivers. If there's only a little dissolved stuff in the water, you can probably see the bottom. If there's a lot of dissolved stuff in the water, you probably can't. Finally, the transmittance depends on how far the light moves through the substance. Anyone who's gone swimming underwater knows this is true. We see that water is transparent, but it does absorb some light. The deeper you dive into the pool or the ocean, the darker it gets, and the bottom of the ocean is very dark indeed. Beer's Law tells us how much light will be absorbed based on these 3 factors. Here is the associated equation, A equals epsilon BC. Let's look at the factors on the right side. Epsilon is what we call the molar absorptivity coefficient. That's basically something that tells you how much your substance absorbs at that wavelength. As a side note, sometimes you'll see this written as a small a instead of an epsilon. The next quantity, B, represents the path length. Remember, the amount of light that gets through is dependent on how far it travels through the substance. The farther it travels, the more light will be absorbed. Finally, we have C, which is our concentration. The more stuff you have dissolved in water, the more it will absorb light. Why do we use absorbance rather than transmittance in Beer's Law? Because increasing amounts of stuff cause the transmittance to drop off exponentially rather than linearly. For example, here we have an aliquot of substance that has a transmittance of 90%. If the light has to pass through another similar aliquot of substance, it will lose another 90% of what entered the second swath. So the total amount of light that gets through to the other side will be 0.90 times 0.90, or 0.90 squared. And you can see that if there's a third similar aliquot that's added onto the far side, we're going to lose another 90% of what came out of the second swath, so our total transmittance would be 0.90 cubed. Using absorbance, which remember is the negative log of the transmittance, allows us to make the relationships in Beer's law linear rather than exponential. Scientists like me love linear relationships because we can graph them easily. So again, here is Beer's law. A equals epsilon BC. We use this in lab in a couple of ways. First of all, if we know the molar absorptivity coefficient of a compound at a given wavelength, we can use it to find the concentration of a solution containing basically nothing but that compound. How would you do this? Well, you'd start with a cuvette of a known size. The width of that cuvette would tell you the path length, B. Then fill the cuvette with your solution and measure the absorbance. At this point, you have values for absorbance, molar absorptivity coefficient, and path length, so you can solve for the one unknown variable, concentration. But that's really only useful for very specific situations. Often, as I mentioned, you'll be looking at a mixture containing a lot of things, not just the compound you're interested in, a substance we will refer to as our analyte. There may be compounds in that solution other than your analyte that absorb at the wavelength you're measuring at. For example, you might be analyzing how much blue food dye is in your sports drink, but there's not just blue dye in there. There's also sugar, electrolytes, and of course, water. So how can we accurately quantify just the concentration of an analyte? Basically, we're going to use two different techniques. First, using a matrix blank, and second, creating a calibration curve. Let's talk about blanks first. The purpose of a blank is to help you measure only the analyte you're interested in. How to make a good blank could be the topic of a video in and of itself.
For now, just know that a matrix blank will contain everything in your sample that's not your analyte. In the case of our sports drink, a matrix blank would contain water, sweetener, and electrolytes. Everything but the blue dye. When you do UV vis labs, your blank will include pure water because it's your solvent, plus all of the reagents that you would add to that sample before analysis.
During the experiment, you'll put your blank into the instrument for analysis first. The absorbance will be measured and set as a baseline for any subsequent analyses. In other words, the absorbance of anything other than your analyte will be quantified and subtracted out. Now let's talk about calibration curves. When we're examining an unknown sample with UV vis spectroscopy, we don't always know what the molar absorptivity coefficient of our analyte is, but we can find out. What we're going to do is make a series of solutions that have a known concentration of our analytes and measure their absorbance. We then plot them on a graph that has absorbance on the y-axis and concentration on the x-axis. Despite its name, a calibration curve is not very curvy. Remember Beer's law, A equals epsilon BC? Well, epsilon is a constant for your specific analyte and wavelength, and if you're using the same cuvette for all of your measurements, the path length is also a constant. So this means your observed absorbance should be a constant times your concentration. In other words, in an ideal world, your calibration curve should be a straight line. You can use the linear fit feature in your spreadsheet to determine the equation of this line. Because you have absorbance on the y-axis and concentration on the x-axis, this equation gives you a relationship between absorbance and concentration, one that you can use to determine the concentration of an unknown. The design of a good calibration curve deserves a video of its own, but hopefully this is enough to get you started. Let's summarize what we've learned in this video. Transmittance tells us what fraction of light entering a sample makes it through to the other side. Absorbance is the negative log of transmittance. Beer's law shows us the linear relationship between how much light is absorbed, the chemical nature of the analyte, the distance the light travels, and the concentration of the analyte. By using analytical techniques like creating a matrix blank and a calibration curve, we can use Beer's law to help us figure out how much of our analyte is present in an unknown solution. Do you have questions? If so, leave them in the comments below, and I'll try to address them in a future video. Thanks for watching. I look forward to seeing you again soon.